Oh, thank you very much. I'm glad there were some people before me, so I know how to hold the mic. Yeah, so I'm Thieme Hennis. I was educated at TU Delft as a system engineer, focusing on social technical systems. Most people ask, system engineer, it's very technical, but my interest is in social technical systems. Get involved after the talk. So that eventually led me to get hooked to a couple of guys working for Border Sessions. Who knows Border Sessions? Yeah, fantastic. Who went to Border Sessions this year? Okay. Some people did. Well, Border Sessions is also exploring different futures, merging technology and society, utopian futures, where we want to go, but also dystopian futures. With speakers, and this year we had over 30 different labs, which is a one-day event focusing just on one specific topic. And these were like, I was involved in a lab that looked at using AI and other technologies to make ecologies, regenerative ecologies, more independent and autonomous. So ecologies speaking for themselves through technology and having more autonomy. And also another lab focused on just very more engineering and design approach for developing ecologies in the North Sea and using technology to grow coral, for example. So it can be very technical, can be very conceptual, arty. It's just a very nice mix. And we love ThingsCon. I went to ThingsCon as well with Casper. Yeah, you organized the lab over there. So, talking about the future. So, 2 years ago, the European Space Agency gave us some money to connect more with a maker, entrepreneur kind of community with a couple of suggestions or areas for research. And one of them was inspired by, does this work? No, I thought it was maybe, no. Anyway, Melissa, that's one of our partners. And they were interested in developing technologies that would enable us to live outer space. So that's something that I will talk about in this session, and also the project that I work on with Sydney, who's also here in the audience. He's the lead technical engineer. This is more or less the context. So I haven't seen the movie, but I did read the book. It was fun. It actually was. It read like a movie, like a Hollywood movie. Supposedly, it's pretty scientific. So the context is that eventually we will venture out into space, and when you venture out into places like Mars, you can't just bring or order a pizza or bring your groceries or take everything from Earth. You have to regenerate your the system that we have on this planet to be able to live there. So this is more or less the general context that we're faced with. And the objective was also to connect with the wider community of makers and developers, and also educate and doing outreach. Part of the money that came from the outreach department of the European Space Agency. So mixing education, science, technology development into a coherent program. And so we organized a couple of events. Casper was also involved in that. And we started developing a technology, a prototype, an infrastructure to allow plant science in a distributed and a citizen science manner. So, just one step back, what is Melissa? Melissa has a research objective. First, the acronym. I don't know, who's involved in European projects? Yeah. So there's no European project without a good acronym. So the Melissa means Microecological Life Support System Alternative. And I put alternative in italic. Do you know why? because we live in a life support system, our planet. It's the best of the best. We haven't seen any better life support system than our own planet. So we need to develop an alternative to be able to live on other planets or even in starships. Who knows this? Yeah, just shout. It's called the Biosphere 2 project. Yeah, okay, so there rings a bell. So this idea isn't new. Melissa is quite old, by the way. It started 25 years ago, but this is also quite a established center and established research. Maybe not research. This was founded by people from the performance and arts direction. And these people, and I have a lot of respect, by the way, but they look at the world from an aesthetic sense. So they look at our planet, they see oceans, and they see lakes, and they see forests and deserts. So what they did is they have different compartments, and they have a huge structure, cost hundreds of millions of dollars. And they built a mini ocean, and a mini desert, and a mini forest, and some agricultural land. And they put 10 people in there, or 9. And they thought, okay, let's close it off. Let's see how they go. But yeah, clearly a mini ocean is just a salty pond of water, right? And when you put it next to a forest, maybe things coalesce and start to diverge and don't go as planned. So it was a successful experiment, I would say, because it showed that this is not the right approach, because within 9 months, everything just started dying off. The CO2 levels started rising. People couldn't live there anymore, so they had to escape. And there was one survivor, or at least one species that survived, which was a very nasty type of ant that just ate everything. This is in Arizona, and it still exists, and now there are scientists involved, so it's really producing some good science as well. So this is contrasting the approach that Melissa takes. They have the same, more or less a more demarcated approach and focus. Their goal is to develop a regenerative or a closed-loop life support system where all the human waste, the CO2, the feces, the urine, and non-edible biomass from the other compartments, anyway, and turns it into the basic components for life, which is oxygen, water, and food. And they are complete engineers. So they develop technologies and put it in different compartments as input-output models and look at biological processes, microorganisms, algae, just different biochemical processes to convert these waste streams into oxygen, food, and clean water. And plants are one of these compartments. So you have different compartments. You have the crew, and they produce waste, and then through different compartments, which are all closed and monitored and understood well, and you control these different compartments using environmental aspects. You give them heat, sometimes light, and other controlling mechanisms to be able to, to avoid the issue you had with Biosphere 2. You don't want to mess it up. So I'm going to skip this. This is something for later because I have too many slides. But this is the technical bit, or at least the scientific bit. We are in these are step by step. We are in the higher plant compartment, and plants are involved in producing oxygen, food, and water. So it's a really important compartment, and it's also the one that is least understood of all these different compartments. So I said they were engineers, so this is more or less what their pilot plant looks like. It's aesthetically possibly less appealing than the Biosphere 2 project, but it works and they can control every compartment. And they have been working on this for almost 25 years, or over 25 years.
So these are all the compartments together?
No, this is actually not a complete compartment. Yeah, they have some models in between that simulate different compartments that are not ready yet. And they have on different places, they have different research groups focusing on these different compartments. And we are part of the research group focused on the higher plant compartment. And our goal is to develop a distributed plant lab infrastructure across the world where you can do plant analysis using a low-cost IoT device, a hydroponics kit stuffed with different sensors. But the protocols and the seeds and the nutrition is being supplied by the European Space Agency. So we control for some variables, but other than that, the Melissa and scientists involved are mostly interested in getting a very wide range of data points. So we don't have to put it within a desired closed compartment because they really want to know, okay, if in a classroom in Italy in the summer, the CO2 level rises up to 2000 ppm. Okay, let's see how the plant performs under those circumstances. If there's a holiday and the plant doesn't get, nutrition for a couple of weeks, okay, does it still survive? So hardiness of plants and plant behavior, it's all going into the data sets. And this is more or less a complete model of how you can mathematically and visually describe how plants perform and how they relate to different environmental factors. And this is the goal, the scientific goal of Melissa, to do that, because once you are on Mars or on the moon and you grow plants, you don't want to mess it up, right? AstroPlant fits in that picture. These are the plants that are currently under consideration.
White strawberries.
It's white strawberries. It's I don't know actually. It tastes good. Yeah, it's nutritious and you have to look at the biomass being created compared to the biomass being discarded, and all different factors play a role, but taste is really important as well. It's not fun being on Mars, I think. I don't want to go there. So this is one of the scientists involved. She's doing that in her lab, but she doesn't have the capacity and the skill to do this really on a large scale. So the solution is to develop this network of schools and makerspaces and urban farmers and other interested parties to participate in this research, to get the kit, to learn about space and learn about agriculture, about the technologies involved, because this is, the technology to grow plants on Mars is the same technology being used to grow plants here on this planet. So it's not that much different. You use artificial lighting, you use hydroponics, you use the same kind of nutrition, but it's all happening within Westland, and it stays within Westland. It's a competitive advantage, and we are an open source project, so good. So it's a network of plant labs. This is more or less the overview of what it contains. This is the existing prototype, and we are working towards a new prototype that looks a bit different, but it more or less gives the overview of what it contains. So the second goal was to educate and to do outreach, to enable young people, other people as well, to learn about food production nowadays. So citizen science is a hobby of mine. I really like most of the projects being organized. I've been looking into, I started with SETI and other kinds of projects, Vogelspotten. Is it time? Yeah. Already? So you have different levels of doing citizen scientists. You can use your citizen scientists as bots just to maybe collect one data point, all the way up to using citizen scientists as co-creators, as experimenters. So you saw the list of plants being, under consideration for long space missions. But who knows, somewhere in the Andes there's a very hardy type of soy or grain or whatever that is not yet explored and that is being put in this system. That could happen. If people have good ideas, they can just use the system as well to promote their own studies. So these are some topics that can be, part of an educational experience related with AstroPlant. We did a very interesting project in Ghent last year. We are running, we did a few more this year. The one in Ghent is worth talking about. We went there as a team outing for a weekend. We did a presentation. We met the kids that work with AstroPlant, and we were struck by their talents, and that eventually came out as well. What they did was they extended the kit with their own technology to control for temperature. They developed a pretty good, solid scientific method to research the influence of far wet on soybean growth. And they did many interesting other stuff, including science communication. So it was a very successful project. And this is more than we anticipated. So I blogged about it. You can have a look at the eventual outcomes. It's also open source, actually, their contribution. So, yeah. So these are 2 slides I was given by ESA Education. ESA Education is involved in the project. They develop a large-scale educational project throughout Europe. All the member states of ESA are involved through their A0, which is a network of science education, like NEMO in the Netherlands, institutes. AstroPlant will be part of a program that they are launching this year, and that runs until 2020 with different topics like these ones. Okay, doesn't matter, strategy. It's open source. I guess there are some people in here with technical skills that may be interested. I would say don't talk with me, talk with Sydney over there. Raise your hand, Sydney. He's the super geek of the team, so he knows everything. And we have another person in the Netherlands and one in Switzerland working on the project right now. And we get a lot of attention across the globe, which is nice. It doesn't bring any money, which is not nice, but it's still nice that there's a lot of positive attention for the project. This is more or less a road trip through how we developed. This was the first prototype developed by Arn. I saw him in the list of attendees, but he's not here. Second prototype, we organized a hackathon, and that was very successful. And from the hackathon, the eventual team that now works on the project is still involved. So successful in many senses. And a third prototype that was more done internally with the team. A fourth one, and now we're working on a fifth one, which is actually just the top panel, which can be used as a more, it's easier, it's more sturdy, and you can use it to create your own kit. So It's also foolproof because it needs to be installed in schools, and you never know what happens there. An extension shield, I don't know, this is all technical. This is all custom made, so we have a couple of custom made things, and the rest is off the shelf and integrated into this kit. We have someone in the United States who developed an EC and pH board, which is finished, but he just needs to send us the firmware and the Python code, and he's just unreachable. So if anyone can help us with that will be awesome. Everything is in Python, by the way. So it's a Raspberry Pi based system with an extension shield integrating all the sensors and actuators, all Python based. This is really difficult, really big challenge, but it's really useful if we have multispectral imaging where you can see plant stress and other aspects of the plants, how it performs on an early stage. But we don't have this, but we want it. This is an overview. Okay, so I think this is the story, I guess. Yeah, it is. Okay, so any questions?